Okay, folks. So I sort of misled you last time when I said we were going to pick up with the double integral. In fact, we're going to move to a completely different type of integral. And it's called an iterated integral. And we can see the expression of an iterated integral right here. And again, we're going to call this an iterated integral. Why do we call it an iterated integral? Because you do it in iteration. And you could think of that as you first do step 1 and then you do step 2. So even though we've written it this way, what I'd like you to do is I'd like you to recopy this and rewrite it as the integral from x equals a to x equals b, and then put a big old parentheses here of the integral from y equals c to y equals d of our surface dy. Close that parentheses, dx. So we generally will not put these parentheses in, although I will, as we are first learning how to do iterated integrals, I will put them in for you. But as you go along, you will stop writing these iterated integral parentheses. But this is how, if you think of it this way, it reminds you of how you're supposed to compute it inside out, the way we do everything else when we group them with parentheses. Okay. The basic idea here is that we're going to say that instead of thinking about volume the way I just described it in the previous video, is I'm going to think of volume as an area times a small change in width. So we can think of area times width as giving us volume. And we'll look at why that's so in this example here. So we're going to work this example together. Here I've got, again, this is called an iterated integral. It's different from our double integral from the previous page. This was a double integral. We're going to see, though, in a lot of circumstances, and most any circumstances we look at it in this class, that the iterated integral and the double integral from the last page will give you the same computation. And so in that case, you could think of this as finding the area underneath, the volume beneath this curve over a particular region. We'll talk more about that in class, but for right now we want to learn the mechanics. How do you compute an iterated integral? Okay. So the first thing I'd like to do is I'd like to rewrite this the way I just said that we will sometimes do it until you guys get comfortable with iterated integrals. So I'm going to put a big old parentheses there times the integral from y equals 3 to y equals 4 of our function, which is 4x cubed plus 6x squared y plus 3y squared dy. Close that parentheses, dx. Again, later on we won't write those parentheses. So this is going to be sort of a lie, but I want to look at what we've got inside this iterated integral here, and that's just another integral, except that it's got both y's and x's in it. But as far as the independent variable y is concerned, those x's are just some fixed constant. So this picture I'm about to draw is sort of a lie, but one way to look at this is still outputting a z value for a fixed z value, or excuse me, for any fixed x value. Fix that, maybe call it x equals 1 or x equals 2. For any fixed x value, this function is still going to be outputting a z value. And so it's going to change, though, depending on our choice of y. So I don't know exactly what x value we have currently fixed, but you could see that this is the function z equals 3y squared plus, and then, say we fixed x at something. This is going to be some by for that middle term here. So there's the quadratic term, there's the middle term, and there's a constant term as far as y is concerned. And so even though we don't know exactly what this parabola looks like, we know that it is the graph of a parabola. And so just bear with me, pretend that that's our particular function here for a chosen x value. And then we're going to be computing the area underneath the curve, the net area, depending on the problem, between y equals 3 and y equals 4. So I'm going to do that for a fixed x value, and then I'm going to change my x value to a different x value and recompute it. We'll talk more about that next time in class, but that gives us an idea of how this is similar to computing the volume from the previous page. But for the rest of this problem, I want us to forget about what it is we're actually computing although that's important. We'll see how what that means in class. And let's just focus on the computation itself. So let's return to this problem. Let me get rid of my little underlines. Oop. We lost the 3y squared there. Okay, so now let's go ahead and inside of this integral with respect to x, I'm going to compute the integral with respect to y. And remember, as far as y is concerned, those x expressions, those x variables showing up inside of the function are constants. So this gives us the integral from x equals 1 to x equals 2 of, and I'm just going to simply integrate this function with this function right here with respect to y. So that's going to give me 4x cubed y. How come? Because this is a constant term, and the antiderivative of a constant is just that constant times y. Plus, when I integrate this term, we're going to have something y squared, so I'm going to divide by 2, so this is going to give me 3x squared. Plus, this one's just straightforward integration, y cubed. All evaluated from y equals 3 to y equals 4. And now, don't forget, we have this dx from before. So if you like, keeping with those parentheses, we still have that. So again, I integrated this term with respect to the variable y, and I did everything treating the x's as constants. Okay, so now let's finish evaluating this. This is just really an exercise in algebra. This is going to give me the integral, and this is going to take a little room, x equals 1 to x equals 2. I hope I can fit it all on here, of parentheses 4x cubed times the upper limit 4 plus 3x squared times the upper limit 4 squared plus that upper limit quantity cubed. What did I do? I just plugged the 4 into each one of these y expressions. Close that parentheses. Minus, and then I'm going to plug the lower limit 3 into each one of these y expressions. So we've got 4x cubed times 3 plus 3 times 3 squared plus 3 cubed. And this is still being integrated with respect to x. Okay, so let's see here. This is the integral from x equals 1 to x equals 2. So notice that this gives me 16 x cubed terms, but I'm going to subtract from that 12x cubed terms. So that's going to leave me with 4x cubed terms. This is going to give me 48 x squared terms. And I'm going to subtract from that, oops, it looks like I dropped an x squared there, folks. 3x squared. So let me say that again. This is going to give me 4 squared is 16 times 3, that's 48 x squared terms. And I'm going to subtract from that 27 x squared terms. And so that's going to give me 21 x squared terms. And then for these last two terms, let's see, we've got the constant, that's 64. We're going to subtract from that 27. And that gives us plus 37. At this point, notice that although we started with an integrated integral, we had an integral nested inside of another integral, we're down to a Calc 1 problem. So I'll do this a little bit faster. So this is going to be integrating this gives me x to the 4th power plus 7x cubed plus 37x evaluated from x equals 1 to x equals 2. Folks, you've probably gotten out of the habit of writing x equals 1 and x equals 2 in those integration bars. And I would encourage you for a little while to start putting them back in again. So just finishing this out, this gives us 2 to the 4th plus 7 times 2 cubed plus 37 times 2. And we're going to subtract from that 1 to the 4th plus 7 times 1 squared plus 37 times 1. And when I clean all that up, you should get a value of 101. So folks, again, although we want to talk more about what it is we just computed in class, I've given you a hint, kind of an insight with this illustration here, that we are essentially still computing the volume underneath this surface and the xy plane over a particular region of the xy plane. And so we just found that the volume of this shape here is 101. If I lost you on this aspect of it, I'm not so concerned because that's what we're going to pick up on in class. But for right now, what I want you to focus on is the actual computation step for these iterated integrals. So go ahead and give that a shot and let me know if you have any... Oh, sorry. So there's that one. Go ahead and look it over. Let me know if you have any questions. But then I'd like you to try it on your own. I'd like you to try to evaluate this iterated integral. So here we've got the function xy squared plus y over x. Notice that the order of integration says we're going to do dy first and then dx. That may give you some insight as to where we're going next. Anyway, if you like, you can go ahead and access the answer by clicking on this link if you want to see a worked out solution, or here's what you should get when you're done evaluating this. So give this a shot. Let me know if you have any questions.